In our study of trigonometry, the trig functions, sine, cosine, tangent, and their reciprocal functions all required us to be in the context of a right triangle, or at least we could have created a right triangle and then used the trigonometric functions, right? Can we use the trig functions in a non-right triangle? And actually, it turns out we can. And so what we're going to do is do a little bit of coordinate geometry on a non-right triangle. And so when I talk about coordinate geometry, that means geometry in the coordinate plane. So let's imagine we are in the coordinate plane, and you can do it really in any quadrant, but I'm gonna just imagine that we are in the first quadrant, okay? And so I'm gonna embed the normal non-right triangle in the first quadrant. So this I'm going to call vertex A, and then here we are with vertex C, and then down here I'm going to call that vertex B. Okay, and maybe let's make this a little bit more apparent that it's not a right triangle. Okay, let's call that B. Okay, and of course we got to make it pretty and extend the line. Okay, now when I talk about coordinate geometry, I'm going to call this point B. It's going to have the coordinate, let's see, this is going to be the coordinate C comma 0, and that's because normally when we would label a side of a triangle, right, this side would have length C, and then this would have length A, and this would have length B, right? Okay, easy enough. And then, of course, A would be the origin, so 0, 0. Okay, C, we don't actually know what this is, but I'm going to just call it a general point x, y. Okay, and now I'm going to start digging into this. Okay, I'm wondering how I can represent x and y. Okay, and so if I imagine, um, dropping an altitude is a perpendicular line segment to the opposite side from a particular vertex, but I'm going to drop an altitude from C. So there's my altitude. And in this triangle, right, if I look at this right triangle now, this side length here, so this distance here would be X, and this vertical distance would be Y, right, in order to get to C. All right, so then I'm in a right triangle. Okay, this is fun. Now I can say in triangle, um, in this right triangle A, I don't know what this is, and let's call it P, APC. And if I look at angle A, okay, I'm just gonna, let's call that alpha, actually. If I do cosine of alpha, right, this is gonna equal X over B. And similarly, sine of alpha is going to equal y over b by our trig function that we know and love. Okay, and then, okay, I can solve for x and I can solve for y just by multiplying both sides by b. Okay, so b cosine of alpha is equal to x, and b sine of alpha is equal to y. Okay, well, that's fine and well. What do I do with that? Great question. I'm glad you asked. The other thing that we need to look at is when we drop that altitude, we actually make two right triangles. We made the the right triangle that we just looked at now, and the second right triangle. Okay, so we haven't done anything with the second right triangle. Let's look at that. Okay, well, in this triangle, if I'm looking at the ratio of the side lengths, or the side lengths themselves, I should say, we'd have normally, by the Pythagorean theorem, that a squared is equal to, okay, I don't know how much this is, okay, but, well, actually, maybe I do. I think this would be c minus x squared, okay, because this whole thing would from a to b, that is c units, so, and then I just remove x of those, okay, and then plus, so that would be that side, and then the vertical side squared, y squared, okay, that's fine and well. Okay, let's go ahead and say, oh, now I know that x is cosine of alpha and y is sine of alpha, but sine of alpha, let's just see what happens if I use that information. Okay, so I have a squared is equal to c minus, and then x was b cosine of alpha, okay? The objective I want to do is really eliminate x and y if I can. Let's see what I can do with that. Y is b sine of alpha squared, okay? And now if I expand that, okay, I get a squared is equal to c squared minus 2bc cosine of alpha. That's squared to, just kidding, that is not squared. And then plus b squared cosine squared alpha, okay? And then finally just plus b squared cosine, sine of alpha squared. Okay, and now I'm just going to do a little rearranging. Okay, I'm going to say this is a squared is equal to, okay, I'm going to factor a b squared out of these two terms, and I'm left with cosine squared alpha plus sine squared alpha, and then plus c squared minus 2bc cosine alpha. And we know and love this trig identity. Cosine squared plus sine squared is just 1. So in all, I get a squared is equal to b squared plus c squared minus 2bc cosine of alpha. Okay, and now this formula relates the sides of the non-right triangle that I'm given without even having to worry about x and y. Okay, and this, my friends, is what we call the law of cosines. Okay, so kind of a fun little exploration into the law of cosines, but to do this thing, we need to imagine we have a triangle with vertices A, B, and C, and then we have the opposite side lengths as we had it set up, and then we have this formula. Now, I will mention that the version here has c squared is equal to a squared plus b squared minus 2ab cosine c. It doesn't really matter which order the vertices occur in, as long as you have that whatever side length you have it solved for, the angle opposite or the corresponding angle is inside the cosine. Okay, we have to have that happen. The other ones need to match as well, but you have this version that I found, the second version, and then you also have the version where you have B solved. Okay, I encourage you to write that out on your own. Okay, before I go further, I want to make sure to pay attention to one thing, and that is what do we need to use, or what do we need in order to use the law of cosines? And if you notice, we have C, A, B, and then the angle C. So we need three sides. So we have sides A, B, C, and then angle A. Okay. Now, technically, in order to solve right, one of these is missing. So you need to have one missing and three known. Okay. Now, if we think back to our days of geometry when we were talking about like side, 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 angle, side, we either need to be in the side angle or side, side, side condition, okay, or side angle side, where we have a known angle between two sides. That would be if we knew, for instance, if we didn't know A, we'd have to have B and side B and side C as well as angle A to be able to solve the triangle. So just a little noticing that is going to be very helpful as we work through both the law of sines and the law of cosines. Okay. All right. Anyway, let's solve this triangle as a quick example. Okay, so we have angle B, A, side length A, and side length C. So I always like to put this information into a picture. You know me, I like pictures. Okay, so we have, let's see, angle A, angle B, angle C, or vertices, and then the angles would correspond to the vertices. And so then I'm going to say B has a measure of 61, side length A is 28, and side C is side length 19. So this is the side angle side criterion that I was mentioning. We have two sides and the included angle. Okay, so then first thing that I'm going to want to try and find is side length B. Okay, so if I work with the version of law of cosines that has that side solved, it would be b squared is equal to the other two sides that I know, a squared plus c squared minus 2ac times cosine of the included angle B. Okay. And so I substitute in 28 squared plus 19 squared minus 2 times 28 times 19 times cosine of, what is that, 61 degrees, okay? And if I go ahead and do this, and uh, do the arithmetic, square root both sides, okay, and again, you get a plus and a minus, but triangles can't have negative side lengths unless they're in a particular quadrant. B here is just going to be positive 25.1 or thereabouts. I'm rounding to one decimal. Okay. So great. I have the side length B. Okay. Now, so this is 25.1. Now I need to solve the triangle, which means find all missing angles. Okay. So I don't know, let's find, for fun, let's do side length, or not side length, angle C. Okay. So now I'm going to find angle C. Okay, so in my law of cosines formula, okay, I'm looking for cosine of C, okay, so that means C squared would need to be over here, so then I have A squared plus B squared on this side, and then minus 2AB cosine C, okay, so then now, let's see, I can substitute in what I know, right, so C is 19 squared is equal to 28 squared plus 25.1 squared minus 2 times 28 times 25.1 and then times cosine of C. Okay, so now in terms of the arithmetic, what you're going to have to do is 19 squared minus 28 squared. Okay, move the 28 squared over, move the 25.1 squared over, and then remember the negative 2 times 25 times 25.1, that's all being multiplied, so we need to undo that by division. So subtract 2, and then this is all in parentheses in the denominator, times 28 times 25.1. I encourage you to punch this in your own calculator and confirm that you're about to get what I am going to get. When I do this, I get that cosine of C is 0.74915-ish, okay? So then to solve for C, right, I have to be able to undo cosine. This is where our inverse functions come into play, okay? Cosine is very nice because it has that, or the inverse cosine function is very nice because it has that angle measure being restricted to the angles from 0 to pi, which is perfect for a triangle because we can't exceed pi. And when I do this, I get 41.5 degrees. Okay, I did put my calculator in degrees for this. 41.5 degrees. And generally when we're working with triangles, degrees will be the easiest for us to work with. Okay, so there we go. We have angle C. And lastly, to find angle A, I'd have angle A plus 45 or 41.5 degrees plus 61 degrees is equal to 180 degrees. And so then subtract over and I get angle A is equal to 77.5 degrees. Okay. Another quick check that you should always perform is look at your angles and make sure that the angles and side ratios are in correspondence in that the largest angle is across from the largest side, okay, and the smallest angle is across from the smallest side. So if this is 77.5, yep, that's the largest angle across from side length 28, which is the largest side length. So yep, makes sense. And then our shortest side length is C, so I should see that angle C is the smallest, and that is indeed true. It's a nice little quick check. All right, so there's a introduction to law of cosines. We'll talk about Heron's formula and get some more practice with law of cosines coming up.